Analog circuits. Today we are going to discuss the basics of transistor and biasing. What does it need? What are the external parameters which will affect the quotient point and numerical problems? Next lecture will be like a different type of DC biasing. Okay, so when you look at this slide, you can find two different type of transistor. One is your NPN and PNP. So obviously, you know, by looking the direction, you are finding the types. So no doubt about it, right? So this is NPN and this is your PNP. So how you are saying? Because of this arrow. So when you see the NPN, it is pointing, not pointing towards the base. But when you look at this one, it's pointing towards the base. So I'm not going more in depth. Already you have studied in previous semester. What I want to insist is this arrow is a conventional current direction. Conventional current direction. Conventional current direction. So here I need to say one thing. So this is your emitter and this is your base and collector. So you know this is your for NPN you have electrons, holes, electrons, hot electrons. So how when I am giving a forward bias here, when I am giving the reverse bias, right? So the forward bias in the sense the minus will be connected with the minus terminal battery and plus will be connected with the plus terminal, and similarly the minus will be connected with the plus and here will be connected with the minus and this will be ground. So this is junction 1. I'm not going, see if it will go like a device topic. I'm not going more into just I hope you remember. So J1 is your emitter base and J2 is your collector base. This should be always forward bias, this should be always reverse bias. When you do the biasing, see students, the electrons will move like this, right? The electron will be moving like that. This is the electron current actually. But when you go for a conventional current direction, see like a just opposite to the electron direction. So that is a conventional current direction, emitter, and this is your base. So emitter current is nothing but a sum of your base current and collector current, my dear students, right? So this is about a conventional. This arrow, very important. See, the collector current is always looking the emitter current. That you keep in mind, very important when you draw the molding. And also see the electrons, it's moving away from your you can see here. See, here what happening is the conventional current direction, everything I said. How electrons are going like this. But holes are moving away from the base. So that's why I said this is a conventional current direction. So you know conventional current direction is just similar to the same as a here whole direction. So that's why it is away from your base. Okay, so this is for construction of your NPN, and this is your back-to-back diode model. So you have to be very clear with that, right? So when you put for NPN, this is N and this is your P and this is your N. See, negative, then this is a positive and this is a positive. Back-to-back diode. The emitter base is connected to the forward bias and collector base is connected to the reverse bias. Okay, so these things are very important to understand the further topics. So about this DC analysis, the question is, what is a linear amplifier? So it will come suddenly in your mind. So take some system. This is a system you consider. When I am applying a signal, see, you will see the magnified output. See, if you see both the signal both are same in terms of signal representation, the phase or your frequency or it's same. Even the magnitude is raised, but representation of signal is same as your input and output. But when I am giving another representation like this, see the some part of the signal is clipped out and the representation of the signal is not same as your input. So if the output is not same, is a replica of your input, there is a non-linear condition. So as a engineer, what we want to design is linear amplifier. So what are the steps and procedure to be followed to design the perfect linear amplifier circuit? So linear amplifier means your signal should not clip out either in the positive end or negative one. See, other name of DC analysis is a loss signal analysis. While you are doing the loss signal analysis, you need to consider AC source is 0. That means during the theoretical assumption of a DC analysis, you want to consider your AC source is 0. Okay, where you want to fix the quotient point, that is a question. So that we will get the answer in the coming slides. What is the Q point? It is an operating point. It is an operating point. It is an operating point. So operating point. What is the operating point? It is a point at which the signal will be starting to swing. So if this is your AC signal, this is your DC point. This is what your quotient point actually. Okay, so the slides, whatever is prepared, is everything from chapter 5, bipolar junction transistor, Neamen. The name of the book is Microelectronics Circuits or Electronic Circuit. Author Neamen. So you can follow same. So now it's a very important slide. It's a very basic. What are the four mode of operation? So when you see the four mode of operation, basically see the base emitter will be always forward bias and collector base will be always reverse bias. Please remember, my dear students, always J1 I am taking emitter base, it should be forward bias. J2 is always reverse bias, is collector base. Collector emitter is not a port actually. Collector emitters are not a junction. You have to be very clear. The collector emitter is a port, output port, where you are taking your output. So based on the movement of the charge carriers, you have a different mode of region. The first mode is your forward active mode. The forward active mode, see, I will just draw the characteristics just to understand this mode. I will just represent with your output characteristics graph. So IC is your output current and VC is your output voltage. You know, when you are studying the output characteristics, you want to keep a different set of input current and you want to observe your output current, the changes of VCE. That's what you studied in the previous semester, right? Same I set here. And here the forward active mode, that means this part. What do you mean by it? It is an active region. It is called active region. This region is called active region. This region is called active region. So most of the application, 95% of the application mostly will work in the active region. So the thing here, what you want to understand is the base emitter is greater than 0 and collector base is less than 0, or in other ways, the base will be greater than emitter and base will be less than your collector. So this is a two condition to be followed when it is in the active region. Right? So basically when it is in the active region, it will work on the amplifier application. It will work in the amplifier application. It will work in the amplifier application. So that is very important. So you stick out of the mind, like in the active region, it will work like an amplifier. It's amplifier. That's you want to remember. Don't forget. Okay, now when you go for a cutoff region, see this is a cutoff region. Basically, this point is a cutoff region. In the cutoff region, both the junction will be a reverse bias. See even at the polarity, this point is connected in the forward bias in terms of polarity. For example, the base is connected with the positive or negative is connected to the negative. So see in the polarity wise it was forward bias, but it didn't get the enough voltage to drive this diode. Basically, you have a diode here. It didn't get the enough voltage to drive. Basically, you know the 0.7 voltage is the voltage for silicon to drive for the diode, right? But it didn't get the enough. That's why I'm saying it's a cutoff region. So you want to understand that aspect also, right? So polarity wise you should not see. So you want to see whether the device will get the enough voltage to drive or not. If it didn't get the enough voltage, it is a reverse bias. Okay, that to be very clear. So in this condition, the base will be less than your VC and base will be less than your BE. Okay, so this you want to be very clear. So this is a cutoff region. This will be acting like a off switch, off switch, off switch, off switch, off switch. When go for a forward bias, your base will be greater than your collector voltage and base will be greater than your emitter voltage. The both will be a forward bias. So see generally we used to say like a VC will be in terms of 0.2. Up to the 0.2 it will be in the active region, this point. See this point. In this region, both the junction will be a forward bias, like a junction 1 and junction 2. In that two, the collector emitter voltage will be like a 0.1, 0.2. That is the range. It will be in the generally it will be in the saturation. That will be in the linear region or saturation region. Okay, that is like as a closed switch. In the closed switch. Okay, so this is the thing you want to understand. Finally, the last mode is your inverse active mode. See, inverse active mode means we will not use many application for this mode, but you want to understand. See, actually, when you go for a forward active mode, this one, how the electrons will move? Electrons will move like a emitter to base and base to collector. But when you go for a reverse active mode, what you will be assuming? The electron will be moving like a collector to base and base to emitter. Okay, but when you go for a conventional direction for NPN, like a forward active mode, you will be considered like a collector to emitter. But when you take for a inverse active mode in terms of conventional direction, we will take like a emitter to collector. So that is a difference you want to assume here. So keep in mind that in the forward active mode, the conventional current direction will go from the collector to emitter. Collector is looking towards the emitter terminal. So the forward active mode, it's acting like a amplifier condition. So that is a very important to observe from this slide. So now we'll go for the very important slide, the continuation with the last part. See, in this cutoff region, I said your base will be less than your collector voltage. The base will be less than your emitter voltage. See, this will be acting like a open circuit. So current will be 0. Okay. When you go for the saturated region, the base will be greater than your collector voltage. Base will be greater than your emitter voltage. Say it will be acting like a short circuit. It will be like a on switch. Okay, on switch. So, but we are not interested to work in this region. We are interested to work in this active region. Why? Because your base current is amplified by beta times. Your output current is nothing but a product of beta times of IB. That is, beta times your current is amplified. So this is a region which you are expected to work. It is active region. So here you know the condition, the base is greater than your emitter and base is less than your collector. Okay, so this is a condition to be followed when you are working in the mode of configuration. Okay, so this, please understand, these modes are not externally configured. This is a based on the movement of the charge carrier. This is happening inside your when you are applying your biasing. Okay, this is what you should understand clearly. Okay, so now I'll show the very important diagram. What is the need of quotient point actually? See, just see the first figure. I'm choosing the quotient point near to the saturation region. What happening is the positive part of the output current is clipped out. See, you want to understand first. This is your output current for a common emitter configuration. Please remember, for our entire course, we will be working mostly with your common emitter configuration. I will touch lightly about other configuration. So mostly we will be traveling with your common emitter configuration only. So output voltage is VC and input current is your IB. So you can see the positive part of the current is clipped out and negative part of the voltage is clipped out. So while you are choosing the cutoff, while you are choosing the quotient point in the near to the saturation region, while you are choosing near to the cutoff region, see the positive part of the voltage is clipped out and negative part of the current is clipped out. So this is not a linear, right? This is not a linear. So what I want to do is, I want to choose a quotient point in between the cutoff region and the saturation region, exactly in the active region, so that I will get full swing. You can see the full swing. This is what I expected. So, but practically what is the difficulty is, for example, if you take a common emitter circuit, you know the current equation, master equation, output terminal current IC equal to beta times of IB plus 1 plus beta times of ICO. You know this is the equation you studied in the previous semester. So ICO is directly proportional to the temperature changes. How much time it will differ? If current temperature is increased by 10 degrees Celsius, the current will be doubled. It will double for every 10 degrees Celsius. Similarly, the VBE will be decreased by 2.5 millivolt for every degree Celsius. This will indirectly affect your IB. So if these parameters are changing, your IC also is going to change. See, I have fixed, initially I kept the quotient point in the 30 degrees Celsius. If temperature is changing from that normal case, this quotient point is going to change. So first, initially the quotient for the circuit, when you design a circuit, this is affixed to the quotient point. But due to the external parameters, this is changing. So if it change the quotient point, whether it will move nearer to the cutoff region or saturation region. So that's what I showed. If it is move away from this center part, either the positive part or negative part is clipping. So what we want to do is, as an engineer, we want to design such a circuit, the quotient point to be stable, and we have to recover your old quotient point. It should be free from your clipping. Okay, that is your main thing, that why you want to study this different type of DC biasing circuit. See, another parameter is beta. The beta also is changed. For example, I have designed with the 50. Then some case it's not working. The transistor is not working, so I want to replace to some other transistor and have the beta of 150. So consider if I am changing 50 to 150, I'm not aware of it. So what happened? Your IC also is shifting. So entire design is changed. So you want to redo the design. It's a complicated process. So we want to design such a circuit and should recover your old quotient point so that you have a proper swing. So that is a condition to be addressed why you want to design a DC biasing circuit. So generally, what is the parameter? I said clearly, the ICO, VBE and beta. And repeating again, the ICO will double for every 10 degrees Celsius. So if consider I am working in the 30 degree, you have 2 microamps. If I change to 40 degree, what happened? You are 2 microamps to be considered as 30 microamps. That is double. So 30 or 40, it will double. So VB is for every degree Celsius. So every degree Celsius, 31, 32, 33, 34, 35, Every time the minus 2.5 millivolt is decreasing, that means it will affect the input bias so drastically. So that will change your base current also. That everything to be considered. So beta is your amplification factor, and is your HFE value. Its beta is vary from 100 to 5000 based on your fabrication. Okay, so this is what very important. So this everything is basic. Okay, it help you. It's going to help you to go to the higher end topics. So now we'll come to this very important common emitter circuit. I'm making clear we are studying with the active region. Why you want to work with the active region? Because that region only it will act as a amplifier. Okay, so when you see this circuit, you can see this is biased with the VBB and it is biased with the VCC. What is the biasing? It is an external DC supply which is connected to the transistor to drive the circuit. So here VBB, why I kept VBB is very simple, just to remember. It is connected to base, so just for remember I just kept VBB. So it is connected to collector, I just kept VCC. Just for my understanding, it's not a mandatory, you have to remember. RB is a biasing resistor which is connected to the base terminal, and similarly the C is connected to the collector, it is a loading part. So load resistor which is connected. So you can see the current, this is a C. Another thing you can observe here, so all the terminals, the current denotations are, it is given in the capital. Then because we are working in the DC analysis, in the DC analysis all representation should be in the capital letter, please remember. Okay, so the RB and IB, so you can see it is a conventional current direction, that's why the direction is go from the minus to plus. This is also conventional current direction, that is also going from the collector to minus to plus, lower potential to higher potential. See, you can see the two current is entering, the emitter current is leaving. So emitter current is nothing but a sum of your base current and collector current. Okay, so you have to be very clear in that, my dear friends, you have to be very clear in that. So this is your junction voltage and this is your output drop port. So this is a junction 1, this is a junction 2. So base emitter will be always forward bias and collector base will be always reverse bias, you keep in mind, always don't forget. So when you look at the second circuit, so this is a DC equivalent for this given common emitter circuit. So here very simple, first we will put for this this dotted line, I will explain. In between base and emitter, you know you have one diode, right? So that diode only you are represented here. What do you mean by VB on? The VB on means it have an exact voltage of 0.7. It have the capability to drive. If the voltage is less than 0.7, it don't have the capability to drive. In order to specify that, mention specifically VB on. It's not a mandatory say. Only in this circuit it was given to make you to get a clear understanding. That's it. Okay. When you go for IC, you know it is working in the active region. It is amplified by beta times of your IB current. Right. So see, you can see here beta times of IB, and you want to understand this is a dependent current. So the output current is respect to the input current. The amplified time by beta times. I am repeating again. IC is respect to the active region, you know the beta times of IB current is amplified with respect to that it was given. The arrow is coming from collector to emitter. The collector is looking emitter, so you have to keep in mind. And this is your input biasing, and it is your collector biasing, and RB resistor is limiter resistor connected to the base terminal, and collector is just only the thing is this in the skeleton of the transistor was redrawn with respect to the DC current concept, and I hope you understood this model, right? So now let me go for some formulas. So how this is you see to see all the module have a equation. So it's not possible to memorize all the equation. You want to first have a clear mindset of how to apply the KVL and KCL in the given circuit. Then only you can play with any type of given models. So basically, if you see how that IB is coming, so very simple. First, what we will do, I will erase all the content. Okay, so now we will derive what is IB. So when you apply the KVL, you apply KVL in the input side. What will get? Minus 2 plus KVL, Kirchhoff voltage law, minus 2 plus, so plus VBB. Entering at a plus, leaving at a minus. Why? Because this is a passive element, polarity is not fixed, It is a polarity we want to assume actually. So I am considering like entering at a plus, leaving at a minus. So I am considering the minus for my equation. Okay, it's up to us whether you can then it's a starting end or leaving end. You can anything you can follow. So here the polarity is fixed already. So entering at a plus, you can see the loop is entering at a plus and leaving at a minus. You can see now. So minus. So this is entering at a plus, leaving at a minus. So we will be getting IB times of RB minus E equal to 0. From this I can find IB, I can find RB, anything. So I can find IB. So here you can see IB RB are taken to the left side and they have got this equation IB equal to VBB minus VB on divided by RB. That's it. Similarly, when you go for this output equation, so I'll draw here. So very simple. So just you want to be very clear with your output. KVL in terms of KVL, that's it. Okay, so apply KVL. So what will you get? So plus VCC. So plus VCC means how it will be generally how it will be. So in the circuit you will be having like this. So I'll draw it here. So I am applying KVL in there like this, minus to plus. Okay, so in that only this plus is coming here. So here you have a resistance entering at a plus, leaving at a minus. So minus ICRC. Then entering at a plus and leaving at a minus. So minus VC equal to 0. So with that I have written VC equal to VCC minus ICRC. So this is the equation which I obtained from the output KVL equation. So another equation IC equal to beta times of IB. I hope you are clear on that. Okay, the power dissipated in the transistor, basically the power is nothing but a product of voltage and current. Here the transistor you have a two product, that is a like IB into VB on plus IC into VC on VC. Okay, so this is the exact equation. When you go for the good approximation, you know that VBE will be very very small. So VC will be very larger. Similarly in terms of current, the IB will be very very small and IC will be larger. So with that approximation I can remove this product and I can write the power dissipation of the transistor is approximately equal to IC times of VCE. So this is a good approximation that you can use solving the problems. Okay, so this is the first problem. So I will be teaching you another problem 1, problem 2, that this lecture will be over. Okay, so you can practice. I have one simple problem that you can try which is relevant to this. Okay, so in this problem actually what we want to find is we want to find the base current, collector current, emitter current for the and collector emitter voltage for the given common emitter circuit. Why I am saying it's a common emitter? You should be very clear in that, because the emitter is a common to the input terminal base and the output terminal collector. So that's why it was a common emitter circuit. That please remember. It's not like a you want to understand the meaning. What is a common emitter? The common emitter in the sense the emitter is common to the input terminal and the output terminal. That is why it is a common emitter circuit. So the beta we are considered to be 200. Okay. So basically what is the objective is, so first we want to find the input characteristics, then you want to go for output characteristics. So input characteristics, what is the input characteristics? IB versus VB. So what you want to find is you want to find the load line and you will be having the curve like this and you want to fix the quotient point. This quotient point is IBQQ. So this one only you want to do. Another thing, the output characteristics IC versus VC. See, in the most of the problems you will be asking to find only the output characteristics. Input characteristics only for this problem, just to make you to understand. Okay, so here also you will find maximum collector current, maximum DC voltage, and you will be drawing the DC load line and you will be fixing the quotient point. So the quotient point will be VCQ and ICQ. Okay, so here basically I want to find IBQ and maximum base current, maximum VB voltage, and maximum IC current, maximum VC voltage, and partial current of IC and VCQ. So only you have to be very familiar with applying the KVL. Okay, so basically, so when you apply the equation, okay, so already I said how this equation you apply. By applying the KVL in the input side, you will get this equation, and again I put, so apply the KVL. So here you have a VBB, so plus VBB, entering at a plus, leaving at a minus. So you will be having IB, RB, and entering at a plus and leaving at a minus. So you will be having minus VB and equal to 0. From this equation was written. So your IB is nothing but your VBB minus VBE divided by RB. Here VBB is 4 and VBE is 0.7. RB is 220 kilo ohm. So have a practice and the calculator, then only you will be getting the fine current. Okay, otherwise you will be getting the wrong current value. So 15 microamp, how you obtain that? You have to take a calculator and you have to practice. Sometimes students will write 15 amps, so it is wrong. So you want to consider unit. It's a very important, right? So if you not consider unit, completely is going to be wrong. Okay, this is your IBQ. So similarly, you want to find for IC, you know the IB, so multiply with the beta, will be getting the ICQ value. Then VCU, when you apply the KVL, so that is the VCC minus ICRC minus VC equal to 0. I said in the last slide, say. So VC equal to 10 minus IC into RC, you will be getting 4 voltage. So emitter current equal to base current plus collector current, you will be getting 3.02 milliamps. So most of the quotient point, everything you have determined. Now we will go for finding the maximum current and voltage point. First we will start with the input. See, I said clearly, when you are studying the input characteristics, you will be plotting for input current versus input voltage. Okay, so IB versus VBE. So another thing you can see here, it is given in the microamps because the base is very thin region. The maximum current it can produce in the terms of microamps, not in milliamps. So that one to keep in mind. So IBQ, how you find? You know already. The IB formula is VBB minus VB divided by RB. So from there you can find. Now I said clearly, you want to find this maximum voltage and maximum current. How? From this equation we can find. You have an equation that is IB RB equal to, this only I am rewriting, VBB minus VBE. See, while you are considering finding what is the maximum voltage, you want to consider IB is 0. So VBE, VBB is equal to VBE. So what is the VBB? VBB is a 4, so that is going to be VBB. You understand, right? So VBB is equal to VBE. While you are considering IB is 0. Similarly, when I want to find your IBE, I want to consider VB is 0. So VB is 0. So what is the formula for finding IB? So formula is VBB divided by RB. So you will be connecting, you have this upper point and lower point, and you connect this. And already you got what is the IBQ. So with that you can connect your load line. That's all. I hope understood. The IBQ is 15 microamps. Microohm is 10 to the power minus 6. So I hope things clear. So to find a maximum voltage, I want to consider IB is 0. Formula is VBB equal to VBE. To find a maximum current, I want to consider VB is 0, and we will be getting a equation of VBB by RB. That's it. So now we will go for output characteristic graph. When you go for the output characteristic graph, same procedure, but versus the output current is IC and output voltage is VC. So already you know what is the ICQ, already you know what is the VCQ, already you know what is the IBQ. So IBQ is your input current which you are applying, and ICQ is output current which you are getting from the amplifier, and VCQ is output voltage. So this is a quotient point IBQ. I hope you understand. I am saying again, the IBQ is a point at which the signal will be starting to flow. You can see here this is a point at which signal is starting to flow. Above only the AC signal is flowing. So that's called operating point. So while I am fixing the quotient point, you will be getting the linear condition. But due to some external parameters, it will try to change whether in the upper or lower. So when it move nearer to the saturation or cutoff region, some part of the signal will be trying to clip out. So we want to recover from that condition. For that reason only we are going for DC biasing circuits. So you can see here. So how to find a maximum VC voltage? How you have a equation that is VCE equal to VC minus ICRC. To find the maximum VCE voltage, consider your IC is 0. Consider IC is 0. So then what is the formula? VCE equal to VCC. You know already. What is the supply voltage? Supply voltage is 10. So keep the dot. Keep the dot. Okay, keep the dot. So you got 1 point. Okay, now I want to find what is IC. To find IC, you want to consider VC is 0. Consider VC is 0. So IC equal to VCCB RC. So you will be getting the current of 5 milliamps. So you can see here it is given clearly. So I kept dot here. So I am connecting these 2 points. I am connecting these 2 points. Now already you find what is ICQ. You can see now. So here this is ICQ 3 milliamps and VCQ is 4. I want to plot it in the graph. So this is your ICQ and this is a VCQ. So you want to plot for x comma y. In the x is your 4 comma 3. That is VCQ comma ICQ. So that is your complete understanding from this input load line graph and output load line graph. I hope you understand. So I am saying, if you are fixing the quotient point here, you want to take immediate next line and immediate down line. So from there only you will be getting your output voltage and output current. Okay, so always you will be considering your VCE will be half of your supply voltage. It's not a mandatory in all case, but approximately we will be considering most of the designs. VCE will be 50% of your VCC. Okay, so this will be a forward active mode, this will be a cutoff region, this will be a linear region. Okay, so this is a 3 mode which will operate in the normal mode. So there is another mode called reverse active mode that will work from like a collector to emitter. Okay, this is a conventional representation. I hope everything is clear. Now I will go for the next problem. Same problem, just you have a dual battery. So you can try it and just give the idea. Same formula. Okay, and so we'll proceed to the problem. So very understand is you want to know how to apply the KVL. So when you apply the KVL in the input side, what you are getting? VBB, IBRB, minus VBE, minus IERE and minus V minus. How I am saying minus because they are taken the this term parameter to the right side. That's why this minus are become plus. How? Start from here. So I will write here plus VBB, entering at a plus, leaving at a minus. So what will get? Minus IBRB, entering at a plus, leaving at a minus. So what will get? Minus VBE and entering at a plus and leaving at a minus. So what will get? Minus IRE and this will be entering at a plus and leaving at a minus. So minus V minus. So voltage is minus 1.8. Okay. So from this equation, when you take to the left side and you take to the right side, so this minus will become plus. So IBRB, so plus VB plus IRE plus V minus. So this is the equation I have written here. Okay, so I hope you understand. Okay. So any doubt? Any doubt you can put in the comment box or you can discuss in a class. So from this formula, IB, they have taken this, I will explain. Okay, so here they have done one substitution. So very simple. So we know that IE is nothing but a IB plus IC. What is a IC? Beta times of IB in the active region, you know. So IC equal to beta IB you take outside. So you'll get 1 plus beta times of your IB. So you want to substitute in terms of IC equal to beta times of IB. Okay. So so now we know that IE equal to IB into 1 plus beta. Okay, so now you want to substitute in this equation and you want to take your RB outside. So I will teach. Okay, very simple. So what you can do is you take this, substitute this here. So if you substitute the IB will common, you can take outside. So if you take outside, so you will be having like this, right? So RB plus 1 plus beta times of RE equal to VBB minus VBE so VBE then minus V minus what I want to find? I want to find IB. So bring this 2 down. So that's how you get this equation. You can find IBQ. And this is ICQ formula and this is IEQ formula. So from this we can put the input characteristics and output characteristics. Now I am applying the KVL in the output side. So I am explaining step by step. I hope you understand. So apply the KVL in this loop. So minus 2 plus VCE. Okay. So minus 2 plus V plus. And this is a minus ICRC, minus PCE, minus IERE, and minus B minus. Okay, when you rearrange the equation, so you want to find I am repeating again, B plus ICRC minus VCE minus IERE minus V minus. So what I want to do is I want to take your VCE outside because I want to find what is a VCE. When you take to the left side, you will become B plus minus of minus ICRC minus IERE minus V minus. Only the minus VC is changed to plus VCE. From here I can find what is the VC point. It is 1.59. So and you can rewrite this equation. Okay, you can rewrite the equation to find the VCQ values. Okay, in terms of beta also. Okay, so you know already what is your IE. So IE is nothing but your beta IB into 1 plus beta. Okay, so what is your you can substitute here. Okay, also you know IB is nothing but your IC by beta. So that IC will come outside. So I hope you understand. See here only what happened is IE is nothing but 1 plus beta times of IB. Step 1 I have done. Then in terms of IC I want to change because I want to take this IC outside. So what I can write is 1 plus beta. What is the relation you have between IC and IB? So IB I can write like a IC by beta. So with this only they have written here. So IC they have taken outside. So here you have one IC, here you have one IC. So this is equivalent to this one. So you can take IC outside so that you will be getting this equation. So we can substitute different IC current and we can see what is the VCQ value. Okay. So you can see here, you can already said how to find a maximum formula. VCE equal to VC minus ICRC. To find this point, you want to consider IC is 0. So you will be finding VCE equal to VCC. Here, similarly here, you want to consider VCE equal to 0. So that you will be finding VCC divided by RC plus RE. Okay, so already you have an equation. So you have an equation. Okay, so you have an equation. This is a main equation. From this you can draw the output graph. You can try, and you can plot your VCQ point and ICQ point. Okay. Hope this is clear. Okay, so and also you can try with the different beta values, and you can see how the quotient point is shifting. Okay, so that you can check. Okay, so in the next class we will be discussing the bipolar transistor biasing. Okay, so what we are going to discuss in the next class is, so we want to see, already I said the quotient point is changing. How we can avoid the changes? Even the external parameters are changing. So we have many type of biasing circuit. Fixed bias, that is a base resistor biasing, collector to base biasing, and modification of fixed bias and base resistor biasing, and collector to feedback biasing. And following that, you have an important circuit, voltage divider biasing. So we are going to discuss only the two important biasing circuits. It is a base resistor biasing, also called as fixed biasing. That one, and is a voltage divider biasing. Both we will be explaining in the next class, and how to fix the quotient point. Everything we will say. What is the problem with the fixed biasing? Why we want to go for divider biasing? That everything we will be discussing in the coming lecture. I hope you got a clear idea and why you are going for this type of circuits. Okay, I hope you got some idea. Okay, thank you for this.